Okay, hi everyone. Shall we start? So today I'm going to talk about, welcome to the exercise class. I'm going to talk about these exercise sheets, one signal problem. So hopefully it won't be as large as the previous exercise sheets. So I'll just decided to put it in one problem. And this problem is also, as previous ones, is connected to an actual research problem that is, so the paper is not even out there, so it's still going on. And so what we're going to look at, it was already mentioned in the lecture, that of course we have this Landauer's principle when it comes to the cost of erasure and the cost of erasure as expressed in the change of entropy. But for quantum systems and for particular settings, we can actually write the exact equality. So not just an inequality as usually the Landauer's principle is expressed, but also an equality. And we're going to look at two settings. So the first setting we call a coherent setting, and it will consist only, and we will look at the following global system, which will consist of two parts. So the first is the system S, which is a target system that we want to cool down, and the machine M. And the machine M is, so if I draw this, then here we have the system S, then we have a system M, and M is connected to a bath of temperature beta. Also, whenever I say temperature beta, what I actually mean is inverse temperature beta, but I'll just say so for the sake of being short. And so initially the machine is in a thermal state of this temperature. And then we want to see, so our idea is to see how do we connect the change of the energy of the machine and the change of the entropy of the system. Exactly. So what is the difference? Okay, so let us start with some preliminaries. So the joint state of the system and the machine is first this uncorrelated tensor product state, rho S, and the machine is in a thermal state for temperature beta with the Hamiltonian HM. Of course, we assume that the temperature is beta is non-negative, just to keep ourselves in this physical setting. And then after the transformation is described as a unitary acting on this joint system. So after the transformation, the state of the system S and the machine M is some rho Sm prime, which is just a result of acting with this unitary. And of course, we label the reduced states as just rho S prime and rho M prime. Another quantity that we will need is the mutual information, the final mutual information between systems S and M after the transformation took its place. So this is the mutual information, which you've already probably seen in the quantum information course. At the end, it is defined as S of rho S prime plus S of rho M prime minus S of rho Sm prime. And one thing that we will not prove here, but this is a fact that we just take for granted from quantum information theory, that is that the mutual information between two systems is never negative. So it is always non-negative. But this I will not elaborate on here because this should have been a part of the QIT course. And also the other quantity that we will need is something that we saw in the previous exercise class. It is a relative entropy, but just our normal relative entropy in the sense of Shannon entropy. And this is a relative entropy of the final machine state with regards to its initial state. So d of rho m prime relative to rho m, which is, just to remind you, is usually defined as trace rho m prime log rho m prime minus trace rho m prime log rho m. Okay, so these are essentially two quantities that will allow us to turn the Landauer's principle into its equality version. Okay, so before we look at this equality, let us first just observe a following fact. So let us prove a following lemma. So let us look at the following. So let us sum the changes of entropies of individual subsystems. So the change in entropy of the subsystem S plus the change of entropy for the subsystem M. So we claim that this is equal to the mutual information between systems S and M, the final mutual information, which is bigger or equal than 0. So this fact is trivial to see because we have an advantage in how we chose our initial state of the system. Our initial state of the system is a product state, which means that we can just add the entropies of respective subsystems. So rho S of rho SM is just the sum of entropy of rho S and entropy of rho M. Okay, and moreover, we know that the entropy of the system does not change if we apply a unitary operation. So the entropy of the joint state of S and M does not change after application of the unitary. Okay, and then the fact becomes quite clear because the left-hand side of our lemma, so let us say that here we start the proof. So left-hand side of what we want to prove in our lemma just reduces to the following. So we have S of rho S prime plus S of rho M prime minus sum of rho S of rho S and S of rho M, which is equal to S of rho SM prime. And this is equal to the mutual information of the final state, which is non-negative. Okay, good. So this was the first step. Now let us turn to the main theorem, which establishes the equality, or the form of Landauer's principle where we can state equality. So I claim that the following holds. So beta trace HM rho M prime minus rho M minus S of rho S minus S of rho S prime equals I S and between S and M, some mutual information between systems S and M for the state rho SM prime, plus the relative entropy between rho M prime and rho m. So the final and the initial states of the machine. So this is our Landauer's principal equality form. How does this relate to our usual inequality form that we used to see? So we can note here again the information coming from the QIT course that both the mutual information between systems S and M and also the relative entropy between the final and the initial state of the machine are non-negative. For any states that we plug in there, which essentially means that here we have on the left-hand side the change, the change of the energy of the machine, and here we have the change of the entropy, and here we have the coefficient beta, which we can divide over and put it into our entropy. And then, of course, given this, the fact that the change of energy minus the change of entropy is greater or equal than 0, we get our initial inequality Landauer's principle. Okay, so now let us prove this. This will be pretty easy with the lemma that we just saw. So what does our lemma essentially tell us? So from lemma, it follows that we just rewrite it in a more convenient way for us. So S of rho S minus S of rho S prime plus the mutual information in the final state equals to S of rho M prime minus S of rho M. On the other hand, we know exactly what the initial state of the machine was. So it was a thermal state at the temperature beta, and the Hamiltonian of the machine, we also know it is just HM, right? So we can just say that because rho m is the thermal state, temperature beta, Hamiltonian HM, then we can actually explicitly write its entropy. So S of rho m is beta trace HM rho m plus log trace e to the power minus beta HM. So this just follows from the fact that rho m is e to the power minus beta HM over its trace. Okay, and so because we can write it out, let's just plug it into our equation here, which we gotten from lemma. Okay, so let me copy this when I go to the next page. Paste. And also how the row of S of rho m looks like. Okay, so we just plug it in. And what we get is S of rho S minus S of rho S prime plus the mutual information equals the following: S of rho m prime minus beta trace HM rho M minus, log trace e to the power minus beta HM. Okay, so now we, to get to the equation that we need to get, let us add and subtract the following. Beta trace HM rho M prime minus beta trace HM rho M prime. Okay, and here what we get is the following, so we can group this term and this term to get the desired term in our equation, which would correspond to the change in the energy of the machine. So that we can write that this is beta, sorry, I highlighted the wrong term. Of course, we need to use the first one. We need the one that goes with the plus. So what we get here is beta trace HM rho M prime minus rho M. What we are left with is the following. S of rho M prime minus log trace e to the power minus beta HM minus beta trace HM rho M prime. Okay, and and the next observation that we have to make is the following, that actually D, the relative entropy of rho M prime given rho M, can be written is equal to the following. So minus minus S of rho M prime minus trace rho M prime log e to the power minus beta HM over trace beta e to the power minus beta HM. So why is this? Because if we just write our entropy here out, we just left with minus rho M log, plus rho M log rho M prime minus, here we have plus plus trace rho M prime log rho M. Is this correct, or is there a minus somewhere? Let me see. There should be a minus. So, yeah, I see. So here we have to write the plus anyway. All right. Yeah, here we have to write the plus, because then we can write here the minus, and then it's exactly the relative entropy between the states, rho M prime and rho M. And then we also see that actually this this equation here is minus the equation which just appeared in our sum up there. So this part. So here we just add some exponential and then take a logarithm of it. And then we get essentially this part. Okay, and from this it follows that our initial thing that we wrote almost on the top of the page here is equal to the following right-hand side. So I just rewrite it the left-hand side. And here we regrouped the right-hand side in the following two terms. So the first term is the change of energy of the machine. And the second term is minus relative entropy. Okay, and like I'll rewrite this, but here we already can see that this is exactly the equality that we wanted to prove in our theorem. So to see so, we just group the components corresponding to the change of energy of the machine and change of the entropy of the system on one side, and then mutual information and relative entropy on the other side. So doing so, we get the following. So here we get the change of energy minus S of rho S minus S of rho S prime is equal to the mutual information plus the relative entropy which is non-negative, which I already mentioned in a comment in the beginning, because both of these measures are non-negative, whatever you plug in there. Okay, so this concludes our proof for this coherent setting, where we're just considering two systems, the target system S and the machine, and then they undergo some unitary, and then we can write actually exactly how the change of energy of the machine and the change of entropy of the target system are connected using these two measures. Now let us consider a more involved setting, which we will call an incoherent setting. So and this setting is different from the previous one by the fact that here we want to model the work that is done in this process more explicitly by saying that our machine actually consists of two parts. So the first part is kind of a hot part, and the second part is a cold part. And so you can imagine that this machine is actually a small Carnot machine, where there is this cyclic process of passing the heat from the hotter object to the colder object. Okay, and for this, and we will see that for this formulation, we can also connect exactly what is two quantities. The first quantity is the change of the free energy of the target system S, and the second quantity is the change of energy of the hot bath, and connect them with the change of the entropy as well for all three systems, and also the relative entropy as previous time for both baths. Okay, and so this limit we will call Carnot Landauer limit, because it's basically us modeling explicitly the work by a Carnot machine. So here the setting is, so we have a system S, And then the machine has two parts. The hotter part we call H, and it is connected to a hot bath at the temperature beta H. And the colder part we call R, and it's connected to a colder bath with the temperature beta R. And since they're connected to these baths, of course, the initial states of both R and H are thermal with respect to their individual Hamiltonians. And so all these temperatures are positive, and the temperature of the hot bath is bigger than the temperature of the cold bath, which is for inverse temperatures the other way around. So let me maybe just highlight that they're hot and cold. So this is cold one. And this is a hot one. Okay, so, and now just some preliminaries for the notation that will be used in the equality. So we start with the state rho SRH, which is a product state. A system S is in some state rho S. And the other two are in thermal states at their respective temperatures. Then we apply unitary to the joint system. And here we pose an additional assumption. Namely, we assume that the unitary is energy preserving. So it commutes with the global Hamiltonian. Then we introduce the following labeling. So delta S of some system is the change of the entropy on that individual subsystem. Then delta E is change of energy. Also on some subsystem. And then we also look at the free energy, which we're familiar with from the previous exercises. For the state rho at the temperature beta. This is a trace of H rho of some system minus 1 over beta S of rho. Yeah, just to remind you, it's the same free energy that we were looking at before, because 1 over beta is just kT. Just sometimes we use beta, sometimes we use T, and so on. And also delta F temperature beta for some system will be the change in this free energy. So, okay, I can write it out. F beta rho prime minus F beta rho. Okay, and the last notation-wise is eta. Eta is Carnot efficiency. So in this case, it's one, Carnot efficiency for a Carnot machine with the hot reservoir at the temperature beta H and a cold reservoir at the temperature beta R. So in this case, it's 1 minus beta H over beta R. Okay, and now we are ready to state our equality. And I will not prove the equality. I'll just give a hint of how you do it, and then the rest you can try to solve by yourself in the exercise sheet. But yeah, let me just write it out. So I'll just call it a theorem. So here we claim that the following holds. Minus delta F at temperature beta R of a system S minus eta delta EH, which is the energy decrease in a hot bath. And it can be useful to have how our expression exactly in terms of this change, because hot bath can be seen as kind of an energetic resource one must use or expend to cool the system S, the target system. So it's just like shows how much energy we have consumed cooling our system S. And this is equal to 1 over beta delta SS delta SR plus delta SH, so the change of the entropy on the individual subsystems, plus D, so the relative entropy between the states of the final and the initial state of the cold reservoir, and the relative entropy for the same so the relative entropy of between the final and the initial states of the hot reservoir. And this is, of course, bigger and equal than 0. Okay, so yeah, so this is our theorem. You see that when we are using these two reservoirs, kind of, even though we might not interpret kind of having these two parts of the machine as having a Carnot machine, our Carnot efficiency anyway comes up, and we see that like we only like our usage of the energy coming from the hot bath is only as good as our Carnot machine, essentially, that we have. So it's like it's in our interest to have the cold bath always colder and the hot bath always hotter, so that this efficiency would be maximal. But in any case, it just shows that we can use the energy from the hot bath only up to the efficiency that we can have. Okay, and so to prove this, just use a hint, which I kind of already spelled out in saying that mutual information between systems is always non-negative. And the mutual information that you'll have to look at in this case is the mutual information between three systems, rho, so between three systems, S, R, and H, in the final state, which is defined as just sum of their individual entropies minus the entropy of the joint state. Sorry, I said M. I was just thinking of the previous part. So it was R S R H prime. And this is always non-negative. Okay, so now let me spend the following minutes on how this theorem exactly connects to the Landauer's principle that we discussed before. So connection to Landauer's, like more explicit. So how can we rewrite this equality in terms of like just reduce it to some inequality, so make it in a sense weaker? So what we essentially have here is the following statement, that the energy extracted from the hot bath is lower bounded by the increase in free energy. So this so this change is lower bounded by delta F. So the energy extracted from the hot bath is essentially trace of HH, rho H minus rho H prime, which we label in our previous labeling as minus delta EH. So this is like the energy, the final energy of the hot bath is of course lower than the initial energy. So this indicates how much we have extracted. And it's always lower bounded by the increase in free energy, which here we labeled as delta Fs. So this is just F of at the temperature beta R of rho S prime minus F beta R rho S. Yeah, so moreover, if we also assume that the initial state of the system S, the target system S, is also thermal. So for example, we say that rho S is a thermal state at a temperature beta R and Hamiltonian HS, then the right-hand side of this inequality is non-negative for any process, because we know that like whatever process we apply to the thermal state, the change in the free energy has to be non-negative. Just as one of the properties of the thermal state. So if we start with rho S as a thermal state, then we always extract some energy from the hot bath, and the change of the free energy of the target system is always non-negative. One can also kind of look at this in a different way. The same way we can see the Carnot process as extracting energy from the hot bath, it can also be seen as a process which dissipates the heat in a cold bath. So alternatively, then we have to kind of express the delta EH here via the changes of energy in for a target system and the cold bath, cold reservoir. Okay, and this is true since the energy is conserved. And then we can write that delta SR minus beta H delta ES plus beta R minus beta H delta E R is bigger or equal than 0. Yeah, so you can, like, if you substitute the delta EH by this equation in our theorem, then you can see that you arrive to this equation. So here we just bound the change, lower bound, for example, the change of, or connects the change of entropy of the system R with the changes of energy of the system S and the system R. So here we kind of exclude the involvement of the hot bath altogether, but rather think about the energy dissipating in the cold bath and also energy increase for the target system itself. Okay, so in the exercise sheet, I basically walked you through the most of the exercise sheet, except for the fact that you will need to prove this theorem. But this is done similarly to the theorem that we looked at in the coherent case, where we only had systems S and M. And then by just using this hint that this is always non-negative.